everyone. In this set of lectures on embedded C programming, we are going to take a look at some topics that are in some sense more related to the concept of software engineering and basically about how to develop programs to solve problems and therefore are not just about the art of programming in C itself. So let's take a look at why this matters and how it affects the way that you develop embedded systems. So we are going to start by talking about software architecture. Now, as an example, I'm going to take a case study of a home automation system. So even though I call it a case study, the code that I'm going to show you over here is not real code. It doesn't really do anything specific. It's more illustrative. It sort of shows the typical kind of functions and routines and the structure that you are likely to use when you develop a home automation system. So what exactly do we mean by a home automation system? Well, there are a few things we would like to do. One of them is to monitor the temperature in various parts of the house. There could be other things where we monitor humidity. There could be other sensors as well, for example, motion sensors, light sensors, any kind of door intrusion, anything of that sort, gas leaks, all of those are things that are typically included in the home automation process. But we are going to restrict ourselves, at least in terms of the example, to just temperature and humidity. And the assumption is that you have some way of controlling the air temperature by basically turning on or off the air conditioning. And maybe as part of this, we also want to alert the user to changes, right? And the first question that we want to answer is, how do you even go about structuring such a system? How do you go about developing or architecting such a system? And what I'm going to do over here is look at one possible way of doing this. And I want to emphasize that over here, everything that we are talking about, each of these architecture patterns and the structures that we are looking at are sort of possible ways of solving the problem. And fundamentally, there is no unique answer to all of these problems. Different people, depending on how they go about developing, depending on the language they are developing in, depending on the kind of microcontroller they are using, this kind of sensors, all of that will affect the kind of architecture and the structure that you use for your software. What we are going to do is look at a few different possibilities. We are going to start by looking at one possible way of doing it. Now, a common thing, especially in the modern day approach to how we go about developing software, is that we want a file structure, because the way that we think about programs is that each part of your program is written down in some kind of a file. We think of them as C source code files. Typically they would have an extension like this, main.c or something of that sort. And the moment we look at it, we know that main.c is a file that contains some text, which if you read it will essentially correspond to a C program. And at some level it's important to understand that all of these are conventions, right? There's nothing fundamental about the fact that main.c or even a .c program or a .c file specifically contains C source code. It could perfectly well contain text, it could be a PDF, it could be a movie which is just renamed as a .c file, right? Nothing about the system itself sort of prevents you from doing one or the other. But obviously conventions matter. They help us to structure and to use systems, and therefore we automatically assume that if I see a file called main.c, presumably it contains C source code. More importantly, the main.c is very likely to be the part of the C source code that actually contains the main structure to be executed, or the main function, which gets called first when the C program is executed. Now on the other hand, you can also see that for each of the .c files in this case, there is a .h or a header file, right? Now, why do we need header files? Primarily so that you have function prototypes being defined appropriately. Any kind of parameters that are used in your C source code get abstracted out into the header files. You could have macros which you define in a header file and then use in different parts of your code. The point of all of this is that it helps you to structure your code. And why does all of this matter? The moment you are going beyond one or two functions that you need to call, it makes sense to think seriously about how you are going to split up your code across multiple files and have each file containing one cohesive unit of your source. Now, right at the bottom, there's also this file over here called a make file, right? And what does a make file do? A make file essentially gives structure, or rather it allows you to compile all of your source code and to combine them together into a single executable. We have already looked at the compilation, linking and execution phases of the program. All the steps, what is required in order to compile and then to link, are specified in a make file. This is once again a common approach to do things, right? A make file in general is an example of what's called a build system. In other words, we think of software that we are writing as building a program, which is why you will also see the terms architecture throughout, right? People approach the whole idea of constructing or building, right? There's a lot of terminology here that comes from actually building systems, right? And it makes sense because there is a lot of thought and planning that needs to go into it, similar to how you would go about constructing a building. And in the same way as you have a building, and unless your foundations and your basics are right, your software also is going to fall apart if you don't construct it carefully. So as you can see over here, this is a typical structure. What I mean by that is there will be C files with corresponding header files that contain their function prototypes, data types and so on. There will be typically something which is the main routine that needs to be run. In most embedded systems, you will have a structure where you see that there are sensors, actuators, communication. These are the three main parts of any embedded system. You need to sense something, you are interacting with the outside world, getting information from outside. You need to actuate something, you need to either turn on an LED or turn on a motor or turn off a pump, right? The on off, those kind of activities are essentially how you control the outside world. And finally, you need to communicate all such decisions to some other system. It could be the person who is actually monitoring it, or it could just be a logging system. But these three aspects are the most common parts of pretty much any embedded system that you can think of. Now, in addition to that, almost any system will have some utility functions, things that don't necessarily fall into any one of these categories, but are nice functions which make your code easier to read, understand, modify and so on. And finally, you have this make file that helps you to compile everything and combine it together. So this is the typical file structure in a relatively large software development project. And here we can look at an example of what the actual code looks like. We'll be looking at this a little bit more detail in a moment, but what you can see is this, for example, is what the main.c header, the main.c source code looks like, and this would be what the main.h, the header file, would look like, right? There are certain conventions, this if def, the guards that you see over here are once again common practice to put in header files, right? And the reason is very simple. It basically sort of, if you were to include a header file multiple times while building a system, it can basically complain that you're redefining certain macros or functions or something of that sort. And by having this kind of a guard which checks whether there's a particular variable or a macro that's been defined, and if it is defined, then don't include the rest of the file again, right? So this is once again a common convention. It's not required, but it's common practice. This header file is very simple. It just contains one function definition. And where is that function defined and used? It's here, right, in the main.c source code. Now, there is sometimes a tendency, especially among beginners, to sort of include one C file inside another. This is technically not wrong in the sense that the compiler allows you to do it. It is not, however, good practice in the sense that it makes it very difficult to scale your program, right? Because the moment you include one file inside another and then you include that somewhere else, you can very easily end up in a scenario where you can end up in loops, right, where a file basically tries to include itself through some loop that gets created in your include chain, right? And not only that, it's also makes it much harder for the compiler to actually sort of optimize code, because now it's dealing with a larger and larger expanded or pre-processed file. The recommended way, as we have already discussed, is to break your code into multiple different C files, compile each one of them into a .o or object file separately, and then finally link them together somewhere. Now in this case, we can see that our main function actually looks pretty clean, right? And what I mean by clean, and hopefully you agree on this, is that there's very little code actually in main, right? And that code in fact can be divided into two parts. There is a setup phase where I basically call something to initialize certain functions, and then there is the event loop, right, where basically it's an infinite loop in this case, where I read the sensors, I process the data, I control some actuators, send some status data, and maybe just delay by a certain amount, 1000 milliseconds or so in this case is what presumably we intend over here, right? So this kind of structure is very common once again, especially in embedded systems. Now if you are writing a program whose only job is, let's say, to print hello world, you don't really have this kind of a setup followed by a loop structure. Similarly, if your program is supposed to read a few CSV files, do some kind of an calculation of the average grades of students in different subjects, and maybe plot a histogram and finally exit, right? Once again, you don't really have this concept of a while loop. But embedded systems are typically not those kind of run once and exit kind of programs. They are meant for user interaction, which means that this kind of structure where you have a setup phase followed by the loop phase is a very common kind of pattern that you see while structuring embedded programs. Now this word pattern is something that we'll be talking a lot about as we move forward, but for now the important thing that you have hopefully already noticed is that this exactly resembles in an Arduino sketch what you would have in your setup part of your function and the loop part of the function, right? In fact, if you go inside an actual Arduino program, you will find that it takes your setup and loop and does precisely this, right? It basically expands it out into a larger C program where setup is called once and loop is put into a loop, an infinite loop, which just keeps getting called again and again. So this is sort of the structure of the main routine. What I'm going to do is now very briefly look at the rest of the code, but not go into it in detail. It's only to sort of give you a flavor for how it's structured. So I'm using the walkv interface over here, but quite frankly, this is not a program that's going to run on walkv, right? It probably might compile because it's a C program, and it may even run. The printfs may work. It may be able to put something out onto the UART, but that's not the main purpose of what we are looking at over here, right? What I want to do is to sort of show you only the structure of what the files look like. The main.c we have already seen, right? So it basically has a setup part where it calls a system init function, and it has a loop part which basically goes through a while loop out here. Now inside system init, if you go in, you can actually see that it basically calls a series of functions: init sensors, init actuators, init communication, right? And the point is, none of these are defined in your main.c file. Each of them goes into their corresponding C file, and the definitions themselves are located in the corresponding header files. So if I look at sensors.h, for example, I can see that I have got some kind of a type definition for a structure which holds information about the sensor, basically the current temperature, the current humidity values. How am I going to get those? We'll see. There seems to be one function called init sensors and another one that basically says read sensors, which presumably is how these values of temperature and humidity are going to get updated. You'll also notice that read sensors in this case takes in a pointer to a sensor data structure, and this is again a sort of nice clean way of doing things. Another way would have been that read sensors actually returns an object or a structure, a struct of type sensor data. The alternative is that I create the sensor data once somewhere and keep updating it. In fact, if I go back to this main.c, I'll see that this particular line, sensor data, which is just initialized to 0 in this case, right, acts as some kind of a memory of the system, right? Each time I go through the loop, basically what is happening over here is I'm updating that particular struct, the data struct, processing the data that's present over there. Based on the data present there, I'm going to control certain actuators, and then finally I'm going to send some status information. So the sensing, processing, which actually happens on the CPU, actuating, and communication, broadly the four main parts of pretty much any embedded program sitting inside the loop, are all done on this data which is taken as a input to all of them. Now when it is being sent as an input, you could sort of argue, why not just declare this as a global variable, and then I don't need to really pass it around over here all over the place. Technically you could do that, right? Once again, this is more a question of good, cleaner programming practice. If you need to expand your code and you need to write larger systems, right, it makes sense to sort of have it where each function basically works on some kind of a pointer or a copy of the data, rather than assuming that there's a global variable out there that it can modify, right? So as long as you pass parameters into a function, the function modifies them and then either returns the value or uses a pointer to modify it in place, you have some way by which you can generalize the operations that you are doing, right? This sensor data variable acts as some kind of a state corresponding to the system, right? It is basically it has a concept of memory. There is some system level state, which is the current temperature, humidity and so on, which is stored inside this particular variable and directs the rest of the system flow around it, right? Depending on your background, if you have done other kinds of programming, it could be GUI programming on a PC or a desktop or a mobile, it could be a web app development, or it could be something completely unrelated to computers where you are sort of just trying to build a system where you need to get certain inputs, react and respond, right, compute and respond. This notion of a central state corresponding to a system and a loop that basically checks the state, processes it, updates it, is a very powerful way of thinking about the system, right? And you could even take it to something completely unrelated to computers, like maybe driving a car, right? The current state of the car essentially consists of, is the engine on, is the gear engaged and is it moving forward, what is the current speed, right? And the kind of sensing that happens is the dashboard, which basically shows you all of those values, which gear is it in, what's the speed at which it's traveling, right? The actuators correspond to the accelerator, which would essentially help you speed up, the brake would help you slow down, right? And in that particular case, maybe communication is not really something important, except that yes, the dashboard once again plays an important role in that it's conveying that information to the user, right? So all those aspects are not necessarily limited to embedded systems. This is in general system level design that we are talking about. The software structure that we are looking at is of course related to the specific domain of embedded systems. Okay, so sensors.h in other words define these functions as well as the data type. The sensors.c in turn actually has functions to do the work, right? In this case, I've just left it blank. I basically say initialize sensor hardware. Most likely what this would do would be to do something like setting up the register addresses or the pointers that need to be manipulated in order to read a particular sensor value. We have already seen how memory mapping is used in order to take a particular sensor and map it into the memory space, memory layout, right, of CPU, so that by reading from a particular address we can get data. So the sensors would typically, the initialization of the sensors would typically consist of setting up all of those parameters for later use. Processing data, in this case I have included it under the sensors. It could also probably have been part of main, because after all it's not really part of the sensing itself. This is the actual computation that I'm trying to perform, right? In this case I have something very simple. I basically say, okay, if the temperature is too much, then basically set too hot is equal to 1 and otherwise set too hot is equal to 0, right? Treat it as a sort of boolean value. And I also increment a count, which is again present inside that, just to sort of keep track of how often I have run this, right? What about actuators, right? Actuators.h contains definitions of a couple of functions. It also includes the sensors.h. Why? Because I need the sensor data type. Okay. Actuators.c tells me what to do, right? If I want to actually control the actuators, then I'm going to turn on the fan or turn off the fan and so on, right? And well, you might be wondering, where are turn on fan and turn off fan defined? Well, that's what happens in the utils, right? So certain things like read temperature, read humidity, turn on the fan and so on are ultimately, yes, they do need to use the memory mapping information, the actual actuator information and so on, but they are not really part of the program logic, so to say, right? They just essentially could be abstracted out. And the reason why this becomes very useful is, let's say that you have developed all your code for an Arduino and you then want to switch over to a Raspberry Pi, or you want to go to an STM based microcontroller. You could pretty much just go into this utils.c and change the settings so that the reading temperature, turning on the fan and so on, just those minor changes are made, right? And the rest of the program logic remains exactly the same. So of course, that is the whole point of sort of structuring and abstracting away the different parts of the program, but this is how you would do it in practice. Okay. And finally, okay, we have the communications.c, which sort of tells us how we can send the status. In this case, I'm assuming that's there is a UART peripheral somewhere. We might even end up just using something like a printf statement, which under the hood probably uses a UART anyway. So broadly, what you can see over here is the purpose of this was to show you how the different functions could look, how they could be organized. The key thing to take away over here is this is not unique, right? This is just recommended good practice, and the only real way of learning how to do this is by experience. Look at the code that other people have written, try and infer from that what are the good practices and what were the bad practices, and try and follow them to the best of your abilities. So to summarize, essentially the way that the code was structured was, we have these headers which have prototypes and data types. We have a main routine which has a very sort of common structure that you have already seen, the setup and the loop, right? And the entire program has basically been broken up. It's modularized, right? Modules or functions or modules containing related functions are put together so that they can be used. Okay. So why do we call all of this architecture? Why do we call it software architecture? I briefly alluded to this when we started out. You need careful upfront design and planning, because typically these things grow into fairly large projects. It might start off as a simple home automation system, but the moment you want to be able to incorporate multiple different sensors, multiple different actuators, different logging capabilities, different alerting capabilities, that's the communication aspects, right? And the sheer number of different vendors who might be involved, right? I mean, you might have different kinds of light bulbs, different kinds of sensors, all of which have some interesting variations just to make life interesting, right? You don't want everything to be too easy, right? Once you take all of that into account, constructing a large project requires a serious amount of planning, which essentially corresponds to architecting a building. Of course, we are talking about software, so readability and maintainability of code rather than how strong is the building. In some sense, the strength of your software corresponds to how well or how robust it is, and does it crash under any conditions, right? So we have a lot of desirable sort of properties out here. Modular code, which basically says that we are breaking it up into functions that can be reused. There's a concept of separation of concerns, right, which basically says that the sensor code should do sensing activities. Actuators should concern themselves with the actuators. The communication subsystem should basically concern itself with the communication. I ideally should not have a scenario where I'm reading a sensor in my communications.c file, right? Of course, this is not a hard and fast rule. There may be scenarios where the only sort of meaningful or reasonable way of doing something is to actually read from a sensor in your communications.c file and then respond to it. But having this separation of concerns as a sort of guiding principle can make it very easy to sort of abstract your code to the point where changing your communication system or changing your sensing system becomes a lot easier, because you have taken that into account right from the start. That also means that you have cohesion in your code. Cohesion basically means cohesive code is something which sort of holds together. When you have all the parts related to communication isolated into a single file, all of those parts are relevant to each other and they sort of help to strengthen each other. You can reuse function calls within different parts of the same file and so on, right? It becomes one cohesive unit rather than just having a hodgepodge of different function calls. And at the end of the day, having some kind of configurability in the system, right, which allows you to just tweak a few parameters and change the kind of system that you are building. All of these are ultimately some of the desirable characteristics of well architected software systems. So, software engineering by itself is a huge field, right? It's probably the subject of entire courses that you could, semester long or even longer courses that you could probably take up. There are a lot of aspects out there that are sort of beyond the scope of what we can do in a course like this. How do you go about designing large systems? One of the most important parts of designing is documentation, right? How do you actually document all the steps that you took in order to arrive at a particular design? Version control is something that sadly, especially electrical or electronics engineers tend not to take too seriously, right? We have a habit of just sort of making copies of files, making modifications and hoping that everything works out well. But this doesn't scale to larger projects, and having a good working understanding of how version control can be used can make a big difference to how you actually develop systems. Testing is again a very important part of software development, right? And there are various stages over here. There's something called unit testing, there's system level integration testing, and many other steps in between that can make a big difference to how well your system can be expected to operate when put into practice, right? And finally, how do you actually integrate and deploy this? In other words, every time that you make a few changes in your code, how do you ensure that everything still works correctly and deploy a new updated version? Every now and then you have probably come across a message on your phone saying new firmware has to be downloaded. Depending on what kind of TV or some other such appliance that you have, you might also find that yes, a new firmware update needs to be downloaded and installed on your system. Why is that? Because people have continued looking for any problems in the software, fixing those problems, and then they send out updates. Now, what that means is, how do you test for all of those, integrate and actually deploy those updates becomes an important engineering practice in itself. Of course, in the ideal world, you don't have bugs, right? You just basically write perfect software, it works the first time around, and everything has been taken into account before you deploy. That doesn't happen in practice, which is why we need all of these other steps in order to actually make things work. Now, design patterns, right, are something which have basically come about from years and years of experience with dealing with all of these different aspects of software engineering. And what we are going to do is to basically look at various different kinds of design patterns, both in the way a particular code structure could be used in order to solve a specific set of problems, or in architecting large systems themselves.